So I'm going to be going over my data for my project. So to start, some questions. The questions I want to answer with my data are: Can swing tracking statistics help predict which players will have the highest OPS, which is on base plus slugging? Which swing tracking statistics have the strongest predictive power for OPS? And can a machine learning model accurately identify high OPS players using only swing tracking statistics as feature variables? So here's my data. To CSV where I scrape the data from Baseball Savant. So here's what the data looks like. Each row in this data represents one MLB player's performance for the 2025 season, recorded via StatCast, which is what tracks the data from Baseball Savant. So one unit of observation is an individual player from 2025, and it's only 2025 because that's when swing tracking statistics started. And the observation type is cross-sectional data. So here's what the variables look like. Most are continuous or numeric, except for one categorical variable I made. So some important ones to note are attack direction, attack angle, which is your average attack angle. So think if I'm swinging this way, 0 degrees is here. 10 degrees would be swinging this way at the ball, and -10 would be down. So the mean, as I'll show later, is 10, which is right there. So OPS is the industry standard for showing who the best offensive player is, and it's what fans can understand. So just think higher OPS, better offensive player. So there's some other counting stats like home runs, and then some swing outcome stats. So out of zone swing percentage, so percent of time you chase a pitch that's out of the zone. Overall swing percentage, how often you swing and miss. Some other things like your launch angle average, hard hit percentage, which is interesting to look at, but I'm not going to use for the final model. Swing length, which I think is interesting. So think if I start my swing here, a shorter swing length would be going straight to the baseball, and a longer swing length would be going back, which is kind of how MLB players use this to their advantage. So typically longer swings will have a higher bat speed because you have more time to apply force to the ball. And then average swing speed, which is what I'll be looking at most for this model right here. And I'm not modeling yet. I'm saving that for the project. So the data is structured in a simple rectangular structure. So each row is one player's 2025 season. And then I'll get into what I did for my OPS category variable in my data prep. So the first thing I did is split the data into training and test data, which is what you have to do for your machine learning models. You can't look at your test data in the model. That makes your results better and you overfit. So I use 80% of my data for my trained data, and then I might end up using grid search for my final models, but I just wanted to show that you can do that here. So next, I scaled the data using a standard scaler to z-scores. So this is important for regression models. So for example, if I have, look at my original data, if I have some variables that have smaller numbers, like my attack angles are around 10, and then my bat speeds are around 70. My swing speeds will weight my model more for regression models than my attack angles. So it's better practice to make them all z-scores. That way they all have the same predictive power, which is what I want in this case. So yeah, everything has a mean of 0 and a standard deviation of 1, which is what a z-score is. And then lastly, I created one more variable, which is just an OPS categorical variable, and I'm doing this for prediction. Like I want to see which variables matter for being in the high OPS category, and not just for an increase in OPS. I think that's interesting information to look at. So I chose the top 25% are in the high, and then everyone else is in the low OPS category. So here's some descriptive statistics So something to note, average swing speed 72 with a standard deviation of 2.6, which is a pretty big standard deviation. If you think about 25% of people or 50% of the people are between 70.7 and just under 74. So some other ones, so hard hit percent, around 43% is average. So here we're just seeing the distributions of swing speed. So we have some skew left outliers, attack angles pretty normally distributed, and then OPS has some skew right outliers. You pretty much need to have an OPS of like 0.65 to be an everyday big leaguer. So for the next visualizations, which are correlation matrices and pair plots, I split the data into just standard tracking variables, swing outcome variables, which are what happens after bat on ball happens. So like, did you pull the ball? Did you swing and miss? Etc. Or more so swing decision variables and swing tracking variables. So these are not anything to do with bat on ball and only with a player's swing. So some things to note here. So on base plus slugging and WOBA are very highly correlated because they're both industry standards for how good an offensive player is. They're very interchangeable. So home runs, so you hit more home runs the more plate appearances you have. But the interesting takeaway here was how correlated K percentage and walk percentage are, because typically you hear like, oh, you don't want to strike out, you want to walk more, and sometimes you have guys that are like 3 true outcome players. But as you can see, they're not super correlated with a correlation of 0.19. And then some other interesting ones are swing tracking stats. So average swing length and average swing speed, are correlated with a value of 0.62. And then some things to note, so some of these variables are derivatives of each other, which I just wanted to have in the data in case I wanted to look at. So such as fast swing rate is measuring what percent of the time did you swing over 75 miles an hour. So obviously that's going to be very highly correlated to average swing speed. And then kind of the route at what I want to get at with my data. So average swing speed, if you're a low OPS player, it's going to be around 72. And your 25th or 75th percentile variables are going to be actually lower than the median for IOPS players, whose median is around 73.5. But you can have outliers, so you can see the best low OPS swing speed player is around the best high OPS swing speed player. And then I did similar things with pair plot matrices, and pair plots are cool because you can see the distribution of data along with the relationship, whereas in correlation matrices you just get the value. So you can see on base plus slugging again, very related. Some interesting ones. You can see most of the variables are most of them are somewhat related and have some linear relationship, but a lot do not. So I chose Pearson's R here. I want to highlight the sentence. So Pearson's R was used because the variables are continuous, ratio scaled, and primarily exhibit linear relationships, making it the appropriate choice. And then some things to note for the models I'll be making. So the correlation between some variables does not pose a problem for the techniques I will be using, which are lasso and ridge regression, which already penalize features that are correlated and you use the better one, so especially lasso. And ridge is like a half lasso. So yeah, these are the visualizations I made which I think are very helpful for understanding the data. Thank you.